Good morning to everyone. I am Marcello Pietri, PhD student of the 26th cycle, and my tutors are Riccardo Lancellotti and Professor Michele Colaianni. During this 3 years, the research activity has been focused on a wireless and sensor network, meter, sensor, so devices. In the second year on cloud computing, that is the place on which we send the data coming from these different devices. And then to the large-scale system. Large-scale system that is the basis of the cloud computing. So the research activity has been focused on monitoring on this component. In the monitoring scenario, there are important open challenges. First of all, heterogeneity. We have a lot of hardware, operating system, protocol, software, and different data streams. The second problem is the scalability. We are in the era of cloud computing, in the era of big data and ultra-large scale system. Another problem is effectiveness. This system always requires real-time constraints and sophisticated analysis for a management proposal and so on. And this system also requires resiliency. So no single point of failures are allowed. And also they need dynamic placement, for instance, a virtual machine. And they need also adaptivity. Adaptivity in the sense that no human intervention are allowed in this ultra-large scale system. To summarize, we have millions and millions of devices disseminated all over the world. And we need to monitor this device, this ultra-large scale system, with effectiveness and resiliency. So, we start from the basis, and the basis are the wireless sensor network. We start from smart houses and building automation, from multiple heterogeneous device, large-scale network, new protocols and the operating system like Contiki OS, and so on. So, in the first year of the research activity, we produce an architecture that is able to integrate all these heterogeneous devices and send all the data to the users, also by using a cloud paradigm. So the data are aggregated and these are sent to the users. So what about the result? This architecture is able to collect data from multiple sensors and resources. It supports several communication protocols for both interaction with sensor and data. It ensures the availability of the data collection service. It ensures the scalability up to 100 sensors and meters to cover the large-scale deployment scenario in the wireless network field. And finally, it grants the secure delivery to remote centers. Remote centers as cloud computing, that it is the focus of the research of the second year. So, what is cloud computing? Cloud computing is a complex definition, but from a monetary point of view, we can say that the Google envision for the next years is of 10 million of servers. So, 10 million of servers, we start to monitor from the cluster. There are the smallest component of this ultra-large scale system. So we propose an architecture that is designed to dominate the complexity of the monitoring problem, and that is also designed to avoid the single point of failures. How we do that? First of all, with the decentralization of the monitoring infrastructure. Each cluster is equipped with a standard but independent monitoring infrastructure on it. So, second, we process the data as close as possible to the edge. The data should be initially pre-filtered. Third, by operating in batches, small random frequent operation should be batched to overcome the problem of overhead of small communication if the component is not in real time. And finally, by redundant every monitor component, substantially by using software that is easily replicable. So what about some result? This is the schema of the whole architecture. It It provides a real-time embedded graph for each type of resource with real-time constraint. For instance, we are able to plot a lot of metrics in less than 300 milliseconds. And this architecture also provides, by using MapReduce scripts, a cluster-reduced view that is the behavior of the whole system. So what about the numerical result? For each cluster, we are able to monitor about 3 million metrics per second by using about 5 servers and 8 collectors in a cluster of 1,000 nodes. This is some result. And about the resource utilization, 5 servers and 8 collectors are about less than 2% of resources, while in each single node we use less than 10% of CPU, that is the resources that is most utilized. So, starting from this result, this result led us to ultra-large scale system. So, monitor activity, but not only monitor activity in ultra-large scale system, produce a big quantity of data. For instance, in non-large scale system, 1 hour of ECG electrocardiogram produce about 1 gigabyte of data per hour, while a typical weblog, 5 gigabytes of data per week. In a large scale system, in a single cluster of 1,000 nodes, the monitor activity produces 1 gigabyte per hour by using a simple sampling interval of 30 seconds. If we think a sampling interval of a quasi-real time of 1 second, it's about 30 gigabytes of data per hour. And if we think in 3 days, it's about 2 terabytes of data. It's a lot of data. And which is our objective? Our objective is to minimize the computational cost and also the communicational cost, because monitor activity also impacts on computational cost. Moreover, we want to guarantee the accuracy of information about resources. We cannot take decision by basis on wrong data. So we want to also work with real-time constraints, and even more important, we want to reduce the human intervention in the monitoring process setup. Which is our idea? So I need to introduce something. First, I want to say that in the monitoring infrastructure, the 90% of data are time series, because we are monitoring especially CPU consumption, network consumption, and so on. So only the 10% of data in this architecture are not the time series. So in time series, usually we do an high frequency sampling. For instance, we monitor every second or every 30 seconds. But the problem is that you have a lot of data overhead when you don't need data. When you have load spikes, you catch them, but you have a lot of data overhead. On the other hand, if you monitor at low frequency sampling, the problem is that you miss a lot of load spikes. That is the important thing in monitoring. So our idea is to use an adaptive sampling that is able to understand when there's a load spike and discard all the rest of the information that are unuseful. I'll omit the mathematical details for a reason of time, but I want to also only present some result if compared with the state of the art. We use an evaluation metric that is an average, a weighted average between a quality and a gain, and quality is expressed to an F measure that measure how many peaks we are able to identify, and the normalized root mean square error that is a sort of definition of how our curve interpolate the originated curve. So we use this metric to evaluate the quality of our algorithm. So if we compare with the state of the art, we see the state of the art have not bad performance, but the eval is about the 70%, while in our algorithm it runs from 84 to 88%. So this is a good improvement. And also, if we look at the performance, we see that the state of the art have a high standard deviation. So if you if you fix a sampling interval in the state of the art, you can obtain very poor results. While if you choose one of the parameters of our adaptive sampling, it adapts automatically, and the results is every time good. So, to summarize, our algorithm have a series trend accuracy that is about the 83%, that is very similar to the state-of-the-art trend accuracy, but our algorithm have a peak identification accuracy that is 91%, and the state-of-the-art peak identification accuracy is less than 60%. That it means that the state-of-the-art algorithm, real-time algorithm, miss about the 40% of load spike. This is not possible in a monitor architecture. So we have also a better data compression that is about the 75%, while in the state-of-the-art data compression about the 70%. So by making a simple average, we can say that we have an improvement of about 35%. But even more important, that in our algorithm, the user can decide to give more importance to the compression or to quality of data, while in the state-of-the-art you cannot decide that. And even more important again, that the parameters are automatically chosen in our monitoring, in our adaptive sampling, while in the state-of-the-art this is not possible. And what I said before, that in ultra-large scale system, no human intervention are allowed. So we improve our monitoring architecture also by applying this algorithm, and our monitor architecture now is able to monitor different servers distributed over different data center, over different cluster, and the main novelty we apply to this architecture is a distributed hash table in the middle that allow to monitor service distributed in various data center, for instance, multi-tenancy service. And by applying our algorithm to this architecture, now we are able to monitor about 6 million metrics per second for each cluster. And each cluster now can be composed by more than 2,000 nodes, and we are able to monitor these 2,000 nodes by using only 8 collectors, 5 storage nodes, and 1 root node. That means less than 10% of global resource, also in monitored nodes, and less than the 1% of management nodes in the whole architecture. So, to conclude, my research activity can be summarized by 6 words that are heterogeneity, security, effectiveness, scalability, multi-tenancy, and resiliency. We have proposed scalable, reliable, and open source architectures and algorithms for improve the monitor activity in a ultra-large scale system. Ultra-large scale system that will be not uncommon in a near future. Thank you for the opportunity you gave to me to briefly outline my research activity, and thank you for your attention.